Everyone. Welcome to the Test 2 review session for CS367 Section 1. Um, as the announcement says, the Test 2 will be covering all parts of assembly and a little bit of a linking. That is up to symbol resolution. In terms of slides, this covers from slides 4 to 9. And please note that this actually overlaps with the scope of the test 1. Okay. So the overall theme of test 2 will definitely be focused on assembly. And keep in mind that we are more interested in seeing how you understand assembly and read assembly as opposed to writing assembly. So the vast majority of the questions will be on testing how you well understand assembly, where we only have small, manageable quantities of the questions on writing assembly. Okay. And just like in test 1, I strongly suggest reviewing in class, not only in class materials, but also recitation questions and quiz problems to get yourself prepared. And also, chapter 3 in our textbook has extensive in-chapter problems and as well as solutions to guide you through the understanding of assembly. Okay, to start, let us start with the C language. In order for you to well understand assembly, you should feel comfortable with DC concepts, including 2D arrays, like nested arrays, as well as multi-level arrays, and pointers, and pointer arithmetics, and type definitions, and structs, and as well as unions. And you should also be aware of the relationship between C language and assembly through compilation process, where your C source code is first changed to assembly code file, which is .s file, and then assembly codes are translated to binary file, or .o files, which is basically a non-human readable version of assembly, right? In other words, assembly is a human readable version of machine code or binary file. And then later on, linker basically merges multiple files into one executable file. Okay. There was also something called disassembly, which actually turns object codes or .o files or even executable files into human readable assembly, which was done through a utility called object dump. All right, let's move on to assembly. Our assembly start with the study of assembly start with registers, right? Which are a very small and fast memory which resides within the MCU or CPU. Because of its fast speed, all the computations within CPU, all the computations are actually done through using registers, right? In other words, no computation is done at the DRAM, or of course not in hard disk, right? All the computations are actually done using registers. So everything before before doing computation, every value or every data is copied to register and then computed from there. Okay, where we mostly looked at the 16 integer registers as shown in our textbook, page 180, table 3.2. Among them, there were some special purpose registers like RSP, as shown here, which is the stack pointer. In other words, a pointer that points at the top of the stack. We also had another special purpose register called RAX, which is used specifically to store the return values, right? And also, which was not included in the 16 integer registers, was called RIP, which actually holds the program counter or address of the next assembly instruction to be run. All right, which was related to the function calls, right? As we'll talk later in the review. Other than these are general purpose registers, right? We also talked about some special 1-bit registers called conditional codes. Which was set in parallel based on numerical result of the last calculation, except Leah. We talked about 4 types of conditional codes: zero flag, sign flag, overflow flag, and carry flag. These were used to determine different conditions. Right? We'll talk more about this in the following parts of the review. Okay, let's move on. The basic structure of the assembly is as follows, right? We have operation code followed by source and destination, which is the AT&T format. Okay, so we are learning AT&T format, not Intel. Where the operands, or in other words, source and destination, can have either immediate, register, or memory. One example of immediate is this, which is actually a constant, represented as a constant prefixed by a $sign. Okay, this could be either hex or decimal or whatever. The next type of operand was register, which was indicated just by the percent and name of the register, which represents the register's content, okay, or the value or data that is stored in the register. The last type of operand was memory, which was indicated by a register in parentheses, or which is called addressing mode, which we'll talk in the next page of this review, which treats the register content as a memory address and access that memory address contents, right? Basically, we get the address that is stored in register and dereference the value from there, okay? We'll talk more about this in the next page, okay? Data types in assembly were either integral types or floating types, where we mostly talked about the integral types, so we haven't really discussed too much about floating types. And one important thing is that in assembly, we do not have complex data types or abstract data types like array, structure, union. Okay, so in order to express those abstract data types, the assembly must simulate these data types byte by byte. Okay, and we also talked about control flow. In assembly we only had jump conditionally, or call functions, and return from functions. Right. In other words, we did not have sophisticated loops or branches, like while loop or for loop or if else statements in assembly. So we do not have those branching and loops in assembly, where we only have jump conditionally, or call or return, right? Therefore, in order to express these express this the complicated branching and looping in C language, all the C language branching and looping were translated first into goto form, where goto form is directly translatable into assembly using jump, right? Therefore, by using the direct relationship between C languages goto and assembly languages jump, all the complicated branching and loop in C language is translated into goto, and then from there, it is directly translated to assembly. Okay. All right, let us move on to assembly modes, right? Which corresponds to the part of where we want to have memory as an operand in assembly code, right? Okay, the addressing mode again is to express different parts of the memory as an operand in assembly code. Okay, where the general form of addressing mode is as follows, right? Which indicates address of immediate plus base register plus index register multiplied by scale. Okay, where we have to note that the scale can only be number of 1, 2, 4, and 8, because this is implemented using bit shift for fast speed. Okay, basically what this means is that given this representation, this indicates this part of the memory, right? Computed as follows. Okay. So the addressing modes could have different variants as follows, as shown in this table here. Although this looks like a very there are very many different variants, you don't really have to memorize all of them. They actually follow the same rule. As long as you understand the general case here, and you are able to derive each of the variants just by using your common sense. For example, let's look at this example here, right? Compared to the general case here, here we do not have scale, right? What this means is that the scale is 1. So if you, for example, if you plug in the scale of 1 here, this actually becomes this, right? Let's try this one. In here, you don't have immediate and you don't have base register. What this means is that the immediate is 0 and base register is 0, right? plugging in base register of 0 and immediate of 0, this actually becomes this, right? Okay. This addressing mode is used in the important instructions of move and lia, right? Where the difference between move and lia is that move actually dereferences the memory address expressed in addressing mode, whereas lia does not do dereferencing. Okay, so lia is used extensively for computation, for pure computation, because we get 2 adds and limited version of multiply in one fast instruction. Okay. One thing to remember about move as well, move is that you are able to move from register to register to memory, but not immediate, right? You cannot move you cannot move any value to immediate, right? This doesn't, moving a value into immediate doesn't make sense because immediate is a constant, right? Another thing that's not allowed in move is move from memory to another memory. This is because move is not allowed to do 2 memory references at once. Okay. All right, let's move on. So we talked about branching, as we talked 2 pages ago. So we only have goto via jumps and calls and returns, and so therefore we must phrase if else, while, do while, for, and switch statements, all of them into goto, and then change them into conditional branches or jumps. Okay. Where in the dense and big size switch statement was translated using something called jump table, right? Which enables indirect jumps, right? So what that means is that the jumps table is stored in read-only parts of the memory, where we jump into that part of the memory and get the address of the part of the code that we will jump to. Okay, that's why it's called indirect jump. Okay. So we've talked about different instructions. Just for example, we talked about move and lia, and also we've talked about different arithmetic operations like add, subtract, multiply, right? As well as shift left, right, so on and so forth. All these operations except lia sets something called conditional code, right? Which is again 1-bit special registers that was set parallelly as a side effect of these arithmetic operations, right? Where CF is a carry flag, which indicates, which is set or set to 1 if the last instruction cost carry. So if there was carry, that means unsigned overflow, right? So when carry flag is set to 1, that means there was an unsigned overflow in the last instruction. Similarly, OF, or overflow flag, indicates if the last instruction has caused sign to overflow, right? Note that the unsigned overflow was captured by CF, carry flag, and signed overflow is captured by either signed negative overflow or signed positive overflow is captured by overflow flag. Okay, signed flag indicates if the last instruction's result has a most significant bit of bit equal 1, and 0 flag indicates if the last instruction resulted in a 0 value. Okay. Again, LEA instruction does not set any conditional code. Okay. We've also talked about some of the instructions that does not set any destination values. For example, compare and test are the two operations that is used solely for setting the conditional codes, right? For example, compare QBA computes A minus B without storing the results, right? It only affects CC. So compare and test are the two operations that actually is there to only change CCs, right? Or conditional codes. One thing to note about compare is that the order of the operands are reversed. For example, if we have compare yx, we should think of it as compare x to y. Okay. So suppose if you have compare y to x, followed by jump less than or equal to JLE, what that means is that jump if x is less than equal to y, as opposed to jump if y is less than or equals to x. Okay? So again, compare yx should be understood as compare y to x. Okay? And test instructions computes A and B, which is a bitwise AND between A and B, which is used to check if the value is 0 or signed, for example, right? For example, if you want to check the value in the register was 0, you do test Q and repeat the register twice, and then you jump with the JE, right? As we've seen extensively in our assembly codes, including our binary bombs, right? Following, given the conditional codes that are set through either compare, test, or other operations, we do jumping, right? We do jump. We either do unconditional jump through JMP, or we do conditional jumps using these jump variants, right? Which actually makes jumps based on conditional codes. Although it is important to understand what each of the jump indicates, you don't have to understand how they are computed from different conditional codes. Okay? So you don't have to know, for example, how JE is computed from the 4 conditional codes, okay? Or JL is computed from 4 conditional codes, okay? You don't have to remember all of that. Also, as you've seen in binary bombs, there are the indirect jumps using jump table is shown as jump and followed by the address with asterisk prefix. Okay. Okay. Let's keep moving. There were also set instructions and conditional move instructions, where set instruction is to set a byte to 1 when the conditional is true. Okay. And conditional move instructions was to move conditionally, which was which helped to avoid branching, meaning which helped instead of jumping around different parts of the code with jumps, we were able to use conditional moves in order to replace those jumps. Not all the time, but in some type of jumps we were able to replace with conditional moves. By doing so, we are able to help pipelining of the code, which we'll learn later on in the course. Okay, basically, essentially, what it does was it vastly helps the program to run much faster. Okay, and among the registers, some registers were, by convention, some registers were caller-saved registers, and others were callee-saved registers, where caller-saved registers indicates the registers that has to be preserved by the caller. And callee-saved registers, on the contrary, are the registers that has to be preserved by callee. For example, caller-saved registers, for caller-saved registers, when there is when a function A calls function B, function A is called caller, and function B is called callee. And in caller-saved registers, caller function A, which is caller, should preserve the value of that register. Okay, what that means is that it has to store the value of the register before it calls a callee function B. And then after it returns from callee function B, okay, let me restart. So in caller-saved registers, the caller, which is a function A, stores the value of the caller-saved registers in a stack, right? And then upon returning from the callee, it restores the value of the register. Okay. However, in callee saved registers, within the callee, when the function b callee is called, before overriding the register, it first pushes the value of the register, callee saved register, into the stack, and then before returning to the caller, it restores the value by popping the stack and restoring the register value. Okay. The idea of caller saved registers and callee saved registers is important for procedure calls or function calls, which is governed by stack discipline. So each function call in assembly has its own frame stack, which is its own local range of memory space. Where a stack frame may include local data or local variables or return address, argument variables, and other temporary space. Okay. So let's look into how the function call or procedure call is actually done, including the caller saved registers and callee saved registers. Okay. Suppose function A again is calling function B, therefore function A is caller and function B is callee. In order for a caller, function A, to call function B, callee, this is what it's done at the function A or caller side. So first, caller or function A saves caller saved registers as needed. In other words, if there are some register values that needs to be restored, that needs to be kept upon returning from the callee, then what it does is it pushes the caller saved registers into the stack. Okay. Also, it pushes the first 6 arguments into the corresponding register, which are located for arguments. Okay. If you have more than 6 from the seventh argument, they should be pushed into the stack. Okay. After doing this, we finally call function using call instruction. What this internally does is that it pushes the address instruction after this call into a stack. In other words, it pushes the return address into the stack, and then it jumps to the operands it jumps to calls operand and begin running that function's code. What this means is that it changes the instruction pointer or the register RIP to the value of the address of the instruction in the callee function. Okay. So now again, it replaces again. Okay. So what call function does is that first it pushes the return address into the stack and then jumps to the callee function by changing the RIP or instruction pointer register to the beginning of the callee function. Okay. Okay, let's move on. So what happens at the callee function. So the callee function go through, the first step that the callee function go through is the setup, where it first saves callee saved registers as needed. So the callee saved registers needs to be preserved by the callee, which is a function b, right? So what it does is that before overwriting those registers, it pushes the callee saved registers into the stack. Okay, and then it reserves stack space as needed by subtracting from RSP, right? In other words, it's reserved the stack frame space by subtracting the corresponding amount, byte amount, from the pointer RSP, okay, thereby increasing the stack size. Okay, and then it moves on to the body, where it performs whatever the functions that the function b, or callee, is designed to perform, where it stores the return value into a special return register, RAX. Okay, after that, the callee function finishes. When it finishes, it basically performs the opposite or the reverse operation of what was done in the setup. Basically, it restores the callee saved registers as needed by popping the stack and popping the stack into the corresponding register, which is exactly the opposite of what we did in the setup phase. Also, we return any stack space that was reserved by adding adding the corresponding byte amount back to RSP, which is again exactly the opposite operation of what we did in the setup. Finally, it executes the return instruction, which pops the return address of the stack into RIP, or instruction pointer register, and thereby jumping back to the return address. Okay, and this is literally all that happens, and there's no system involvement. There's no saving all register to some secret data structure somewhere else, so just careful maintenance of our registers and the content of our stack, so that we remember all calculations and remember what code to run next, is all that happens in the procedure calls, or which is maintained by stack discipline. Okay. Okay. After returning back to the caller, a caller simply resumes the function, right? After returning to the caller restores caller saved registers as needed by again popping the register values and popping the stack to the corresponding register values, corresponding registers, and use the the return value, which is stored in RAX. Okay. Let's if we look at how callee works with an example. This actually shows an example of how callee works, right? Where in setup, we push RBX, which is a call save register, and then we subtract OX28, which is 40 in decimal, from RSP, indicating that we are reserving 40 bytes of space in the stack for this stack frame. In the body, we perform something, right? Perform what the function is supposed to do. And then after we perform everything and we store the return address in the return value in our RAX register, and then we finish up by adding back 40 bytes into RSP, and then popping the callee register and restoring our RBX, and then returning. Okay. All right. Okay. So that is how the procedure call works using stack discipline. Okay. We also learned about how recursion works, right? Which actually follows the exactly same procedure, right? So there's nothing special about recursion, although the recursion was treated specially when we learned C, right? However, from the assembly's point of view, recursion is the same as any other procedure calls, right? There's nothing special about it. Okay. The recursion is possible because each function call, even if the same function, result in a distinct stack frame, right? And that's why the recursion is possible in the first place. Okay, let us now move on to the structured data. We've learned about different types of abstract data, including array, struct, and unions in C, and how they are represented in assembly. Okay. Let us first start with array. Array is actually placed in the consecutive blocks of memory physically. For example, if we have L of element A, L of type T, then those L elements or members are placed in the consecutive blocks of memory. Okay. And compared to C, in assembly, everything is accessed in bytes, right? So in pointer arithmetic, if we want to access the third element in the array, what we did was Z plus 3, assuming that Z has the address of the beginning of the array, right? However, everything is accessed in bytes in assembly. So what we need to do in assembly is that to access a third element, what was happening in assembly behind the scenes when we actually do this pointer arithmetic was this, right? Assuming that the size of the element or member is k, then we add 3 times k to z. Okay. We learned about two-dimensional arrays. Two types of two-dimensional arrays. One is nested array and the other is multi-level array. where they look very similar at the C level. However, it was very different at the assembly level. Okay. Nested array is a simple two-dimensional array in C. And if you assume that the type T has a size of K, then the entire array size, if you have R number of rows and C number of columns, becomes R times C times K. Okay, and what is important here is that this type of two-dimensional arrays or nested array also takes up the consecutive blocks of memory, where they are row major ordered, indicating that the first entire row is consecutive memory, and then followed by second row, and then followed by third row, and fourth row, and so on and so forth. What this means is that in order to access the element or member in the ith row and jth column, this is what we need to do. What this indicates is that A is the beginning part of the address, beginning part of the array, where I times C times K is the number of rows, okay? The address of the rows, the address of the corresponding row, ith row, and J times K becomes the address of the jth column. Okay, and correspondingly, to get the value of the element, we access the memory, right? How about multi-level array? The definition of multi-level array was where we have array of addresses that each of the address points at one-dimensional array. Okay. In that case, the address of the ith row and jth column now becomes this, right? What this means is that we first have to access the corresponding address in the address array, and then after we jump to that address, and then we move the corresponding the byte amount corresponding to the column, right? And then the value of the element becomes this, right? The biggest difference between multi-level array and the nested array is that for multi-level array we needed 2 memory access as opposed to 1 in nested array, right? We had to first access the memory in order to get the address from the address array, right? And then the second memory access was to actually get the value. All right. Okay. And then we have learned unions, right? Where in unions, members or elements actually share the same memory space. And the size of the union is the size of the biggest member. Okay. One thing to note here is that if the member is an array, then the array size is the entire size of the array. Okay. So entire array is a member, and the size of the entire array becomes the size of the union, if that's the biggest one. Okay. Since the members share the physical memory space, the endianness effect value, especially when you store as one member and view as another, right? We've learned about this in class. And because of this, because of the same reason where they share the physical memory, bytes are kept regardless of the element access, as opposed to cast in C. Right? Okay. We have also learned structs, right? Where the members of the order of the members of the struct was guaranteed to be kept in the physical memory space, but with padding for alignment requirements. Right? Padding was so that the data does not span two pages in virtual memory, which we will learn in the future lectures, right? So you don't really have to worry about what this is right now. You just accept that this is for fast memory access. Okay, and because of the alignments, what alignment is that each item or member must start at the address multiple of the number of bytes required to store it. For example, if characters, it can start at any byte. However, for 2 byte shorts, this element or member must start at multiples of 2. If it's a 4 byte int, it must start at the multiples of 4 and float as well, and 8 byte for doubles and pointers. Okay. In order to keep this alignment, we had padding or dummy bytes that was inserted in order to fit into the alignment. And the entire struct must have an alignment equal to the largest member inside of it. For example, if a structure has a 64-bit pointer within the struct as a member, then the entire struct must start at the multiple of must start at an address of a multiple of 8. Okay. So due to this alignment, the size of the struct may vary depending on the order of members. In other words, depending on the order of members, the amount of padding or the dummy byte is different, and therefore the size of the entire struct is different. Okay. So how do we optimize the size? The optimized size, or the smallest size of struct, can be achieved when members are ordered from largest to smallest sizes. Right? This is obvious if you think about the alignment requirements, right? So suppose if you align the largest size. So suppose if you have the largest size element first, followed by the second largest element second, and the third largest element third, right? The first element, for example, if the first element was 8 byte pointer, then it must start at the multiples of 8, at the address of multiples of 8, right? And then it will also end at the multiples of 8, right? And then the following one, if it's 4 byte integer, then then it will automatically fulfill the alignment, because it will automatically start at the multiples of 8, right? Which is also a multiples of 4, right? Right? Therefore, by having elements sorted from the largest size to the smallest size, you are always guaranteed to have the optimal or the smallest structure size. Okay. As advanced topics of assembly, we've talked about program memory layout, which is the overall memory structure for the entire program, where it has stack, heap, and data and text, where stack holds local variables and return addresses and temporary values, as we've discussed until within this review, and heap stores dynamically located data, for example, malloc or calloc. And data holds global variables as well as static variables. And lastly, text holds the code or the machine instructions. Okay, and also we've learned the issue of buffer overflow. Okay, this happens because there's no bound checking performed in array indexes. Okay, and some functions in C don't monitor user input length. So the buffer, so the memory address that is allocated for the input may not be enough for the input. In other words, input may exceed the memory space that was allocated to store the input. Then the buffer overflows, and the important data, such as return address, could be overwritten, which causes segmentation error, right? Okay. And sometimes segmentation error happens, and it alerts the user early on, but that was the best thing that could happen when the buffer overflow happens. What's worse was to sometimes jump into different parts of the code by overwriting a small portion of a return address, for example, 1 byte of the return address, or overwriting some parts of some other data without noticing it, right? There are multiple strategies to fight against the buffer overflow. Buffer overflow attack, which actually leverages the buffer overflow, right? At the programmer level, we could use functions with arguments that limits the number of input bytes. For example, fgets or gets, or fgets instead of gets, and string ncopy instead of string copy, right? Okay. And at the system level, there were multiple approaches, including randomized stack offsets. Therefore, in other words, putting random values before the stack. Therefore, making different parts of the code to have different memory address at each instance, right? And having some parts of the code segments to be non-executable, and putting canaries as well, right? We've talked extensively about stack canaries, where a stack canary is basically copying some parts of read-only memory and put it in the stack, and upon returning from the function to check if the value of the canary is kept. Okay. in order to validate that the stack smashing hasn't occurred. Okay. All right, that was the end of assembly, and then we moved on to linking, right? The linking was basically the procedure that links multiple object files into one executable object file, right? Right. So the task of the linker consists of two procedures. One is a symbol resolution, and the other is relocation. Okay. Where symbol resolution was to identify all the symbols in each relocatable object files, right? Where the symbols can be code, for example, function names, or data, like variables, right? In other words, symbol resolution is determining which symbol should be combined to refer to the same spot in the memory. Okay. In other words, simply put, it wants to match each of the symbols into one with one definition. Okay. So different different object files or .o files could have the same variable, for example, that must be matched with a single definition, right? That's called symbol resolution. And relocation is actual merging process of the multiple object file into one file. In other words, combining all text sections, data sections, and so on and so forth. Where the test 2 will only include symbol resolution, where relocation will not be the part of the exam. Before we discuss details about symbol resolution, we've first talked about ELF file, or the short for executable and linkable format, which is the unified format for object file .o files or and executable object files, as well as shared object files or .so file. Right? This should not be confused with the program memory layout of stack, heap, and text and data, as shown here, right? So program memory layout is how does your memory look like? The structure. How is your memory structured during the runtime of your program, right? After your program is loaded, right? As opposed to however, ELF file indicates how your program is stored in your data or in your hard disk, right? As a file, okay? So ELF file has many different sections, including ELF header, program or segment header table, .text, .ro data, and so on and so forth, where you should know what each of the sections store. Okay. .text section stores the code, and .ro data section, which is short for the read-only data, stores read-only data, of course, such as jump tables, right? And .data section stores initialized global variables with symbol information, including symbol name, size, about each symbol. Okay. This contains the initialization value of the data, which takes up space, as opposed to .bss section, which holds uninitialized global variables, right? while .bss section also contains symbol information like name and size about each symbol. However, the variables are uninitialized. Therefore, no space is located for the initialized data, the initialized value, the initial value. Okay. So the only information about the meta information about the symbol, like name and size, is stored, not the initial value, right? That symbol table section stores a symbol table containing all procedure and global variable names, and dot relocation text section has the info about relocating the text section, including addresses of the instructions that must be modified, and instructions for how to modify them. Right? Dot relocation data section has information on relocating the dot data as opposed to the code, right? And dot debug section has the debug information, which is populated by G option in GDB. Okay, let's move on to the symbol resolution. Symbol resolution, as we talked earlier, is about merging symbols, right? One thing to remember here was the rule in merging symbols, right? Where we had strong symbol and weak symbols, right? Where strong symbols includes all the procedures or function names or functions, as well as initialized global variables, right? Where weak symbols includes uninitialized global variables, okay, or global symbols, right? The resolution rules when there are multiple symbols was the link error, right? So there cannot be multiple strong symbols under the same name. Okay. When there's one strong symbol and many weak symbols, the weak symbols will be overridden or ignored, where the strong symbol of the same name will be taken. Okay. If there are many weak symbols, the linker can arbitrarily choose between multiple weak symbols. So the problem occurs when there are multiple weak symbols with the same name, but if they have different data sizes, data types, then this could really incur problems, as we've seen as examples in the slides, right? Okay, so you should understand which are the strong symbols and which are the weak symbols, as we've seen through the examples in recitation as well, right? And you should know how the rules on how the linker selects the symbols, right? Okay, for a symbol resolution, how the linker resolves the symbols. Right? Lastly, we talked about the make utility. How make utility sustains the tree of file dependencies and only rebuilds the file that has to be rebuilt depending on the changed file, the modified file, and the timestamp, right? So the make file only rebuilds the file that was changed, right? Changed and review the file that was only changed, or the file that was affected or dependent on the files that has changed. Okay. So that's it for the review. So so please go over this, not only the class materials, but also the recitation materials as well as the quiz problems, and the questions in the textbook, ideally, right? So that's it for the review, and thank you all for listening, and good luck. Thanks.